Okay, this is going to be part 2 of lesson 2.6 in the AP Calculus curriculum, derivative rules, constant sum, difference, and constant multiple. In this one, we're going to do some examples with analytic functions, with numerics, functions expressed in tables, and some graphs. So let's take a look. We'll start with the functions expressed in analytics. We're going to find the derivative is all we're doing here, using those derivative rules we did in part 1. So let's say if we're looking for f prime of x, and f is expressed as a derivative of x cubed plus 2x squared with respect to x, then that's the same as the derivative of x cubed with respect to x plus the derivative of 2x squared with respect to x. And we're just using the power rule we did yesterday. And so the derivative of x cubed is 3x squared, and the derivative of 2x squared is 4 times x. Remember, we multiply it's outside by the power, and then we reduce the power by 1. So we multiplied what was outside the x cubed by 3, then reduce the power by 1 to get 3x squared. We multiplied on the outside by 2, the power, and then reduce the power by 1. So we got 2 times 2 times x to the first power. If we're going to do g of x and find g prime of x, and that's the derivative of each of these terms, we can take it term by term and get this is going to be the derivative of negative 2x to the fifth with respect to x, plus the derivative of 3 times x to the third with respect to x. Whoops, minus, let's do minus there. The derivative of x squared with respect to x, plus the derivative of 5 with respect to x. And again, we're just using the power rule on these polynomial components. So we got 5 times negative 2 makes negative 10, drop the power by 1 to get x to the fourth. We have plus 3 times 3, or 9, drop the power by 1 to get 9x squared. Now we have minus, we're going to bring the 2 outside, multiply, times x, drop the power by 1. And then recall that the derivative of a constant, 5 is just a constant, the derivative of a constant is 0. So we get plus 0. So the answer here would be negative 10 times x to the fourth plus 9x squared minus 2x. And the next one I want to show you that this works for rational exponents, negative exponents the same. So here we're taking the derivative to get h prime of x. We take the derivative of each term, derivative of x to the negative 2 with respect to x, plus the derivative of 4x to the 1/2 with respect to x, minus 6, whoops, we could do it either way. We could bring the constant out, but either way, derivative of 6x to the negative 3/2 with respect to x, plus the derivative of 5 with respect to x. This is going to be works exactly the same way. We bring the exponent outside and multiply, and then drop the power by 1. So this becomes negative 2x to the negative 3, plus bring the power outside, 1/2 times 4 is 2, plus x to the negative 1/2, and we subtract 1 from the power. Now we got minus, and we're going to multiply by negative 3/2 times 6. Negative 3/2 times 6 is negative 18/2, or negative 9, but we have a negative out here, so that's going to go together and make a positive 9x to the subtract 1 and get negative 5/2 power. And then the derivative again of a constant is just 0. So our answer is negative 2x to the negative 3 plus 2x to the negative 1/2 plus 9x to the negative 5/2, and that's our answer. Now let's look at some in numerical form, where we have a table of values for x, f of x, f prime of x, g of x, and g prime of x. And we're going to find the derivative, the specified derivatives for these values. We're given k of x is equal to negative 3 f of x. Using these rules, we know that k prime of 1, or k prime of x, let's do k prime of x first, is equal to negative 3 times f prime of x. So k prime of 1 is equal to negative 3 times f prime of 1. F prime of 1, we go to the table where x is 1, and f prime of 1 is negative 1. And this is how we do this. So here we've got k prime of x using those derivative rules we just proved a little while ago. G prime of x minus 3 times f prime of x, taking these term by term. So if we have k prime of 2, that's equal to g prime of 2 minus 3 times f prime of 2. And g prime of 2, we're going to look at where x is 2. And we're going to go to g prime of 2, that's going to be 1. Minus 3 times f prime of 2, so x is 2. F prime of 2 is 4. So 1 minus 12 is going to be negative 11. Then let's do k prime of x. The derivative of 4 is just 0. So that's going to be going away. And 2 times f prime of x. So we're going to find k prime of negative 1 is equal to 2 times f prime of negative 1, which is 2 times f prime of negative 1 is 0. So the derivative of k prime of negative 1 is 0. I'm going to erase some of these things up here so that we don't get too mixed up. Over here, we got k of x is equal to g of x plus f of x. So we know k prime of x is equal to g prime of x plus f prime of x. And therefore, k prime of 4 is equal to g prime of 4 plus k prime of 4. And on your open responses, or free responses, you are going to want to make sure you write out expressions like this if you're ever asked to do this with derivatives on that, because a lot of times they will assign you a point just for expressing a derivative like this. You don't have to put both of these lines in there, but at least one of them to show that you're using these rules. So we're looking for k prime at 4, so x is 4 here. We got g prime of 4 is 0, and f prime of 4 is 1, so this equals 0 plus 1, or just 1. Here we have k of x, so we have k prime of x is equal to 3 times g prime of x plus 5 times f prime of x using those derivative rules. We're looking for k prime of 2, so that's 3 times g prime of 2 plus 5 times f prime of 2. We go again, f of 2 and f prime of 2 is 4 and g prime of 2 is 1. So that's 3 times 1 plus 5 times 4. That looks like 23 is our answer there. And then finally, k of x is 6 minus 5 f of x plus 8g of x. So k prime of x is equal to the derivative of 6 is 0. So we have negative 5 times f prime of x plus 8 times g prime of x. We take the derivative. So we're looking for k prime of 0. We go back to the table where x is 0. And f prime of 0 is 2. So this is going to be negative 5 times 2 plus 8 times g prime of 0 is negative 1. So we end up with negative 10 minus, let's multiply, minus 8, or negative 18. And that's how you use tables in these basic derivative rules. Let's do one more example, a couple more examples where we have, let's see, where did the graph go? Not sure what happened there. There we go. Okay, we've got the graph of a function, or two functions, f of x and g of x, both linear functions. Recall that for linear functions, the rate of change, instantaneous rate of change, is constant. So the derivative of f of x is equal to the slope of the line. So the derivative of f of x with respect to x, or f prime of x, for linear functions is the slope of the line. So when we look at this point, where 0, negative 1, and this point on the graph that we can take from it, we know that f prime of x is equal to the slope, which is 3 over 1, or just 3. And for g prime of x, that's the slope of this line. We have the point 1, 0 and the point 0, 2, and the slope there is negative 2. So now we know that for all x, f prime of x is 3 and g prime of x is negative 2. So here we're asked to find k prime of x is going to be 3 times f prime of x. And f prime of x we said is 3, so 3 times 3 is just 9. Here, k prime of x is going to be f prime of x minus g prime of x. F prime of x is 3. G prime of x is negative 2. So 3 minus negative 2 equals positive 5. K prime of x here is going to be f prime of x plus g prime of x. F prime of x is 3. G prime of x is negative 2. So k prime of x is going to be 1. And then we have k prime of x is going to be 5 times f prime of x minus 4 times g prime of x. F prime of x is 3, so 5 times 3 minus 4 times negative 2, which is going to give me 15 plus 8, or 23. And those are how you do examples when you're given graphs with linear functions. Tomorrow we'll learn some more complicated derivatives. Fun stuff.